Now we have median number 1 and median number 2. When we have two materials, we form one interface. Okay? So ideally, this interface is a two-dimensional surface, but we're only plotting the cross-section. So this interface is represented by a single line, but it's actually a surface. Alright? Whenever we form an interface, we need to think, how are the fields classified relatively to the interface? Once you have an interface defined, the forces, the fields, are forced to be classified into the components parallel to the interface and perpendicular to the interface. Okay? So whenever we talk about the boundary conditions, we always have two conditions. Parallel, or called tangential, tangent, or the perpendicular one is called the normal. Right? Once we have an interface defined, fields are forced to be divided relatively to the interface into two different components, the tangential component and the normal components. Okay? If you still remember, the first fundamental postulate tells us, do you still remember? A closed loop evaluation of E field intensity is equal to 0, but this is in the integral form. What about the differential form? The differential is always coming from the curl relation. Okay. The very first fundamental postulate assumes E fields are conserved fields. Therefore, when you make a closed loop integration, it's 0. It's also saying that the E field is conserved. It does not have any curl. A closed loop along these two materials at the boundary, right? So the easiest way to form a closed loop is a rectangle. But I have to make the height, this delta H, extremely small. Why? Look at this evaluation. A closed loop evaluation of my E field intensity means when I form a rectangle, how many sides do I have? I have 4 sides, right? Each side, I'm trying to calculate the line integration of the field with respect to my differential length. So I have one component. This is my tangential field in the second median multiplied by this length, delta W. If I don't make this height extremely small, I actually have to include the normal component of the field inside median number 2 for this part, and the normal component of the field inside median number 1 for this segment, which is very tedious. So the best way is I don't want to include the normal components, and that is fine because I am free to make this height extremely small, approaching 0, but still retaining a closed loop. Okay? So in all these derivations, we have assumed this delta H, the height of the rectangle, is effectively 0. So we're only evaluating this segment and this segment. But in order to form a closed loop, so in this case, the loop direction is following my right hand right? So I'm using my 4 thumbs to denote the direction of the closed loop. So I only have to evaluate 2 line integrations. The first one is segment CD. It is in the direction of my tangential field inside median number 2. But when I'm trying to evaluate the top segment, the differential length inside the closed loop is now having a reversed direction. Segment A, B is now pointing from the right to the left. Okay? But I have assumed my tangential field inside median number 1 still pointing from the left to the right. So when I perform this integration, I need to include the negative sign for the contribution in median number 1. Okay, so there is a negative sign. So these 2 adds up to 0. They share the same differential segment length, delta W. So I can cancel that. So in the end, whenever you have boundaries, the tangential part of the E field needs to be continuous. Due to the fact E fields are conservative fields. So in the tangential components, even across different materials, they have to be continuous. They have to be the same. Okay? So this is very straightforward. The tangential part of the E fields in different materials, no matter how much you have, right? Even in this case, I have one material, second one, third one, fourth one. The tangential part of the E field, they all need to be the same. Okay? So let me erase this one, and let me just draw the direction again. So this is my E1. So I can actually say, this is my ET1, right? This is my tangential component within median number 1. Now that I know, well, the tangential part of the E field in median 1 has to be retained throughout. So I can freely just draw, right? Just draw. Yeah. In all medium, the tangential component has to have the same strength. Okay? Simple and straightforward. Now, if you want to know the angle and the strength, all we have to do is recover the normal components in each medium. So the second condition across a boundary is to find out the normal relationship between the components. Okay? So that is with the help of Gauss's law. As we talked about, well, divergence of D is equal to the free charge enclosed, right? So that means if you form a closed surface and you evaluate the net outward flux, it is equal to the free charge being included. So if we have 2 medium, medium 1, medium 2, in this case we have to form a closed surface. Now in this case, the textbook is drawing a cylindrical surface, but it's fine. The geometry is really not important. So this cylinder with a very short height, again, this short height is very important because you don't want to evaluate the flux along the sides. You only want to evaluate the flux on the top surface and the bottom surface. Okay? Now remember, the surface normal, when you evaluate the flux, is always pointing outwards, which means I have medium 2 at the bottom, I have medium 1 on the top, but the top is having the surface normal of AN2, the second medium, because this one is pointing out from medium number 2. The bottom surface is having the surface normal pointing out, right, from the medium 1 to medium 2. So this is AN1, right? AN1 equals negative AN2 if the box, the surface is really small, right? So when we evaluate the flux, D1 AN2 plus D2 AN1 times this surface, that's my flux, okay? Because AN1 is negative AN2, so I can just change the sign of D2 and use AN2. So in the end, this is telling you, if you have free charge across the interface, you would have different flux density. Okay? So basically, if you have free charge density surface at the interface, you would have different flux density. Okay? So D1 normal. Why do I have normal? Because everything is dotted to the surface normal. Meaning I'm only evaluating the component parallel to the surface normal. Okay? The tangential part is taken care of already because E1t equals E2t. Here, the Gauss's law is only trying to give you the rule for the normal components. Okay? So a very quick recap. Tangential components for the E field intensity has to be continuous. But for the normal component, you're trying to sense the flux density. Okay? If you have free charge density along the surface, then D1 and D2 in the normal components, they don't have to be continuous. You can have rapid change. Okay? That's the meaning of this equation. So let's take a look at a very quick example. If I have a dielectric conductor interface, conductor means metal, so I have dielectric and metal. And again, we assume perfect metal. So the basic conditions of perfect metal still holds. Inside the metal, I cannot have E field, right? So that directly tells you, well, I cannot have tangential field, even in the dielectric. You still remember? That's what we talked about, right? We talked about if I have a metal, the field can only be in a normal direction. So this again is verified through the boundary condition. Because E2, for example, I'm now defining the conductor, the metal, to be medium number 2. Inside the conductor, I cannot have any field, I cannot have a tangential component, I cannot have the normal component as well. So E2t is equal to 0, and that's forcing E1t to be 0 as well. So whenever you have metal, you cannot have tangential field. But you are allowed to have the normal component. So now you have to think, well, interface of a metallic surface, you are allowed to have surface charge density, but still, inside the metal, you cannot have field, right? Not even the normal component. So that's directly telling you d1n is equal to this, and therefore E is equal to d divided by epsilon. Immediately you have this relationship. So this again is verifying if we have metal dielectric interface, even though I can have some charge being deposited, I can only have the normal component of the E field. Because inside the metal, I cannot have any field. Okay? So this is the rigorous proof due to boundary condition to verify that picture. Okay? So that picture is really valid if you have a perfect metal. Right? Second case is probably more practical because whenever we talk about dielectrics, usually we don't have free charge densities. Okay, so these two relations are generic. General applies to all the cases, but now we're talking about special cases. Dielectric conductor, or we have multiple or two dielectrics forming an interface. Dielectrics usually are insulators, so we do not have free charges. So in this case, if I don't have free charge density, that is telling you the D1 normal is equal to D2 normal, right? D1n equals D2n. And therefore, epsilon 1 times E1 normal is equal to epsilon 2 times E2 normal. We have 1, 2, 3, 4 different dielectric media forming three interfaces. From the tangential component, we know they are all the same, and we only need to know the normal component. And that is directly given by this relationship, right? E1, epsilon 1, E1n is equal to epsilon 2, E2n, and you can just continue to write down all the equations. Right? You can write 4 of them. Okay. So this is telling you, no matter how many materials you have, no matter how many interfaces you have, once you know your incident field amplitude and your incident angle, you know everything. You know everything because you know the boundary condition. And the boundary condition is coming from two equations. First, curl of E is equal to 0. E field is a conserved field. And divergence of D is related equal to rho free. So these two fundamental equations tells you a lot. Okay? So in the future, in your examination, I can very irresponsibly just ask you, I give you 10 different materials forming 9 interfaces, and I ask you the outcoming field strength and angle. Right? You're supposed to be able to handle it. Right? But I'm very responsible. I'm not that type of teacher. Okay? So let's go through one example. I have material number 1 having epsilon 1. This is absolute permittivity, epsilon 1. And the second material having absolute permittivity, epsilon 2. I now inject a given E field, E1. Okay? I know its amplitude, meaning the length, and I know its incident angle. The incident angle is the angle with respect to the surface normal. Okay, so this dashed line is the surface normal. And these are two perfect dielectrics, so there is no surface free charge density. Okay? So with all this information, you are supposed to be capable of deriving the field strength and the angle in the second medium. Let's start with the easy part. The tangential component needs to be continuous. So this E1t, this guy, has to be the same. Right? Has to be the same. So the first equation, E1t is equal to E2t. So that means E1 amplitude multiplied by sine alpha 1 needs to be E2 amplitude sine alpha 2. So this is just telling you the tangential part of the E field needs to be the same in the two materials. Okay? Now, before we calculate the normal part, well, this is known, but this is unknown. But if the picture is drawn this way, I want you to think, just by looking at the picture, which material is having a higher absolute permittivity? In other words, is epsilon 2 bigger or epsilon 2 being smaller as compared to epsilon 1? This normal component, E2n, is much, much stronger than E1n. So what is your answer? TA, do you know? No? Do you want to answer? Just by looking at the picture, you had to have a very quick conclusion. Material number 2 is having smaller epsilon. Why? Because a smaller epsilon multiplied by a larger normal component will be equal to a smaller field multiplied by a larger epsilon. Right? So epsilon 2 has to be smaller. That is one point looking from the math. But have we understood the reason why epsilon is being big? If you have a material with a large epsilon, which means this material is very capable of producing induced dipoles. If you have a lot of induced dipoles, they all try to cancel out your external field, right? By making your field weak. So another perspective, another viewpoint is, well, inside this material, it has a very strong E field. It has a very strong E field because this material is not capable of giving you a lot of induced dipoles, right? So you cannot really cancel all the external field out. So if you have a very strong E field, epsilon will be small, right? So this math is just trying to capture D1n, epsilon 1 times the normal component of E1 equals epsilon 2 multiplied by the normal component of E2. So now you divide the two equations and you can find alpha 2, right? Ideally, incident angle, material parameters are given. So basically, just by dividing these two equations, you can know the angle inside the second medium, the field angle. Again, the angle is with respect to the surface normal. Okay? So now you know the angle, all you need to find is the strength. Well, the strength is actually easy because this tells you the tangential part, and this one tells you the normal part. So you just add them together, square summation, and then take the square root. Okay, so this is purely math. But what I'm trying to emphasize is boundary conditions basically tells you everything. Okay? You know the field amplitude and you know the angle. For one medium, you know the full information, no matter how many interfaces you have. Okay? So this is a very powerful tool, and probably the most practical equations you're learning from this class. Right? Boundary conditions are very important. Okay. One last case, and we close this part on set. I have a very long coaxial cable, so this is metal, and I have some dielectric filling with relative permittivity, epsilon r, and I have the outer metal, which serves as the ground. Okay? Ground means the potential is 0. So the inner conductor is having a high potential, V0. This is the case we studied previously. Okay? All we have to calculate is, alright, we have field inside the dielectrics. In the previous case, we have vacuum, but now we have a dielectric filling. Alright, so ER times 2 pi r equals rho L divided. So this is from Gauss's law again. Okay? We can integrate it, right? So the potential as a function of radius. Again, this is working in cylindrical coordinate, right? This is by definition. Potential as a function is negative line integration of E times differential length, dot with differential length. So that's your answer. Okay. For this particular case, because we already know that the inner conductor is held at a high electric potential of V0, so we can replace this R with A. A being the radius of the inner conductor, and that has to be equal to V0. So V0 is equal to this natural log of B divided by A. B is the radius of the grounding metal. Okay? So we can know that the potential as a function of the radius is expressed by this formula. And if you plot it, you are walking from the outer ground and you move closer to the center conductor, you increase your potential. But once you reach to the center conductor, you have the same potential because it's metal, right? Potential has to be the same everywhere. Now look at this result and look at this figure. You have to ask yourselves, now that you have a dielectric filling between the two conductors, what role is that guy playing? You look at this answer, you look at this plot, you don't really know how the material is playing a role in this result. So you ask yourself, what if I increase the relative permittivity of the filling material? What is going to happen? Remember, the material effect is actually included in the potential of the center conductor, right? Epsilon r is included here. So although in the final result, you don't see the material response explicitly, it's actually hidden in here. So when you increase your epsilon r, meaning if you have a filmy material which can give you more and more induced electric dipoles, it is weakening the field strength between the two conductors, and thus effectively lowering your V0, right? So if you have a very good insulator with a very high epsilon R, this V0 tends to become 0, right? If you let this guy to be infinite, this is 0. So what kind of material can give you an infinite relative permittivity? Metal, right? Think about it. So if you increase your epsilon R, you expect to have a reduction in your V0, so the entire curve is reduced. In the extreme case, if you have metal connecting these two metal, it makes sense, right? If you have the entire thing as a one piece of metal, they have the same potential. So this V0 needs to be 0. Okay? So again, I'm trying to say that metals are materials which are capable of giving you the most ideal amount of induced electric dipoles.